Stuff to cover today. We're going to try to play catch up a bit. But before I start with the lecture material, have people hopefully started homework 1? How many people actually started the homework at this point? That's about a third, maybe less than that, of the class. So I'd recommend that you start the homework to the 2/3 of the class who haven't started. I was going to ask how it's going, but I guess it's not so informative to ask that anymore. So there are 5 questions on the homework. You're required to do 4 of them. So I already got some comments that the homework looked very long. But then remember that of the last 2 problems, you only have to choose 1 of them to do, problems 4 or 5. So Barnabas has office hours after class today. We have office hours all next week. So make sure you start the homework and come to office hours if you have questions. All right, so the plan, if we can execute it, is going to be to finish gradient descent today and then start talking about subgradients, because we're kind of on track to cover subgradients today, which is especially important because you guys have some homework questions on that topic, although it wouldn't really have mattered because you didn't start the homework anyways. But all right, so we're going to see how far we can get. So here's what we talked about last time for the last half of lecture, basically. We want to minimize a function f that's convex and differentiable. And it's an unconstrained minimization problem, so we don't have constraint functions at this point. And we talked about gradient descent, which is this algorithm. It's very natural. Basically, we just choose some starting point x0, and then repeatedly we compute the gradient at our current guess. And then we move in the direction of the negative gradient. And how far we move is the step size tk. And we talked about 2 ways to choose the step size. Okay. The first was a fixed step size. And we saw through some examples that we're running gradient descent here. And here's a function whose contours are drawn. The minimizer is at 0, 0. If we chose to start up there, that initial point, that the too large fixed step size, if it was just a constant at every iteration, the algorithm could actually diverge. So what ended up happening was gradient descent kind of just shot back and forth at the extreme ends of the x-axis here and didn't converge to the minimizer. If it's too small, then the algorithm converges too slowly, especially because as we proceed, the gradient gets smaller and smaller. So the effective step size, which is t times the gradient, that's what we move in, that's the direction we move in, that gets smaller and smaller. But with this kind of magical choice of step size, we did fine. We also talked about backtracking line search, which was this way for adaptively choosing the step size. So that means that it depends on the function and its values at every iteration, rather than fixing some constant ahead of time. And it will change from iteration to iteration as well. And there are 2 parameters, alpha and beta here, that kind of control how aggressive we are with the strategy. The strategy basically just has us repeat the following steps. We try a step size t, maybe try, for example, a step size of length 1 initially. And then if the function in that proposed update is bigger than essentially some threshold we set, we keep iterating. We keep making the step size smaller and smaller until we make the function at this proposed update small enough, and then we take that update and we go to the next iteration of gradient descent. Okay, so beta here and alpha, like I said, are parameters. Here is the picture we looked at. Beta is the multiplier that we use at every inner loop of this backtracking algorithm that we multiply by our step size if we don't meet the exit criterion. So if beta is like 0.9, if we don't meet the exit criterion, we try 90% of the step size, and then we check it again. And alpha was the multiplier essentially for the slope of the tangent line that we're going to use as our threshold. And make sure that the directions, like smaller alpha, bigger beta, whatever, that they make sense to you in terms of their effect on how fast backtracking converges. We had kind of a goof last time. I guess by we, I mean the royal we. But I said alpha was the smaller alpha was the more aggressive of the algorithm, but really the smaller alpha is the less aggressive our backtracking exit condition is, right? And beta plays the role that if it's too big, it might take a lot of iterations to meet that condition, and if it's too small, then we might meet the condition early but kind of way overshoot. Okay, so those are the trade-offs you deal with looking at alpha and beta. And that was backtracking. So here was the same example that backtracking basically, it could pick up the right step size at every iteration adaptively, and we converged quickly. Okay, so then there was this exact alternative, but we talked about it and we basically concluded that it wasn't really worth it, so people don't really use it very often in practice. So here's what we want to get to in detail today, is the convergence analysis of gradient descent under the regular step sizes and under the backtracking step size choices. Yeah?
When you do backtracking, how do you know that the step size you start off with is big enough?
That's a good question. So for one, it doesn't really hurt to take too small step sizes to begin with, right? Too big step sizes are what might cause the algorithm to diverge. So if you started off with something too small, then that means that basically backtracking will be slow, but it'll still converge. But that's a good question. I mean, usually people fix values ahead of time that are just kind of standard values. And we'll see that there's a relationship between t and the Lipschitz constant of the gradient. So a good guess would be to start it off near basically 1 over the Lipschitz constant if you know what it is approximately. But yeah, it's a good question. Something to think about in practice. Any other questions? So here was our first result. We're actually going to prove this one right now. So the statement is that if f is a convex function and it's differentiable, and it meets this additional assumption, which is that its gradient is Lipschitz continuous with a certain constant L. So we learned what this was last time. It just means this condition. It means that if I take any 2 points x and y, I look at the distance between the gradient of f at x and the gradient of f at y, that it's no larger than L times the distance between x and y. Then under this assumption, if we were to fix a step size that's smaller than or equal to 1 over L, L being that Lipschitz constant, then gradient descent will converge. So eventually we'll get to the answer, the right minimizer, or a minimizer. And it'll converge at this rate. No matter where we start, it'll converge, and it'll converge at this rate, which is depends on k like 1 over k. So just stare at that statement for a second. Okay. So another way of saying that same result is that if you gave me an epsilon and you told me that you wanted to minimize the function to within a certain level epsilon, so you want that the iterate I actually return to be no different from the actual optimal value of the function by epsilon, then I know that gradient descent scales like 1 over epsilon and the number of iterations needed to get there. Okay? It's just basically saying that if I want to make this smaller than epsilon, that means that k has to be like 1 over epsilon. So if you ask for epsilon to be 10 to the minus 3, I need on the order of 1,000 iterations. If you ask me for another digit of accuracy, 10 to the minus 4, I need 10,000 iterations. So every other digit of accuracy is another magnitude of iterations we need. Okay, so here's the proof of that. We're going to try to go through thoroughly, but also quickly, because we don't have the luxury of taking a lot of time. But here, the key steps are on the slides. I'm going to also write out the proof in more detail on this piece of paper, so you can look at either. But so the first thing we say is that if f is Lipschitz, or if its gradient is Lipschitz, with constant L, then this is equivalent to saying that if I look at the second derivative of f, then at any point x, it's less than or equal to L times I. Okay, that just means that this gradient matrix, the Hessian matrix, if I subtract off L times identity, then that's a negative semi-definite matrix. Or in other words, another way of saying this is that the largest eigenvalue of the Hessian is at most L. That's true for any x. That's equivalent to the gradient being Lipschitz with constant L. So this is something that I hope Aditya talked about in recitation last week. These are kind of, yesterday, I guess. There's a bunch of standard facts about Lipschitz functions and strongly convex functions that I'm not going to prove, but I'd be happy to talk about in office hours or after class, or any of your Ks would be happy to talk about you with them.
I did prove that.
You did prove that. Okay, good. And this is also equivalent to the following very useful fact that we're going to use for the first step of the proof, which is that if I take my function f of x and I do a quadratic expansion around f of x, so this is just the linear term, but now I do a quadratic expansion where I actually stick in L times I in place of the Hessian. Then this quadratic expansion upper bounds the function. So this is true for all y and x. Okay, again, so these are somewhat standard facts that have to do with these properties of Lipschitz functions. So I'm going to draw a picture here as we go along the proof, and hopefully the picture is going to complement the steps of the proof. So let's suppose this is our function. That's, say, our function f we're trying to minimize. And I make this quadratic expansion around some point. Maybe this point here is x. I make a quadratic expansion, and the multiplier of y squared here, if this is a univariate quadratic, is L. And this upper bounds the function everywhere. So this is x, and this is the quadratic expansion, and it's bigger than our function. So now the idea is that, okay, well, we know that gradient descent actually does something similar, and it chooses to minimize that quadratic. So the function at that update of gradient descent has to be no larger than the quadratic is at that update of gradient descent. So if we want to make sure the function kind of decreases sufficiently fast at every iteration, we can just look at how fast that upper quadratic decreases at every iteration, because it always lies above the function. So what's the gradient descent update? It's taking y equals x minus t times the gradient of f of x. Right? And what happens if we plug that into this formula here? It just tells us that f of x plus, right, this is y equals the update, x plus, which is x minus t times the gradient of f of x, is less than or equal to f of x plus the gradient of f of x transpose, what's y minus x? It ends up just being t times the gradient of f of x plus L over 2 times the difference between y and x squared. And that just ends up being t squared times the gradient of f of x squared. So here that's actually a minus, right? I missed a minus sign. It's y minus x, so we still have negative gradient transpose t times the gradient. If this gets blurry or something, just yell at me and I'll change the zoom. Okay, so what's that upper bound? Just rewriting that slightly, that's just f of x. And we have, here we have minus t times the gradient squared. And here we have positive L over 2 times t squared times the gradient. So that's, we can just rewrite that as minus 1 minus L times t over 2 times t times the norm of the gradient squared. Okay, so this is a helpful place to be. Again, in the picture, we just said that how big is the function at the next iteration? Well, it's no bigger than the quadratic is at the next iteration, and that's the value of the quadratic at the next iteration. So that's where the upper bound came from. So why is this helpful? Well, one really simple thing is it tells us that if we take t to be less than or equal to 1 over L, as prescribed by the theorem, then this whole term here is positive, right? I get 1 minus, we have 1 minus L times t over 2 is bigger than or equal to a half. So what do we conclude? We conclude that f of x plus is at most f of x minus 1/2 times t times the norm of the gradient squared. So that means that at every iteration, we're actually decreasing the function value strictly, right? Because this is where we were before. Here's the next step. This is always positive unless the gradient 0, in which case we're at the minimizer. So it tells us that we're actually making progress towards minimizing the function, strict progress at every iteration. Okay, so that's good. So here's where we are right now. So all we've said basically in this picture is that if we take t small enough, then we don't overshoot to the other side of that quadratic, and we get to a place where we can actually bound the function by something that's strictly decreasing. Okay, now let's suppose the minimizer of the function's out here. So let's look at our picture. X plus would have been something near the minimum of that quadratic. X was here. Let's suppose that x star is down here. That's what we want to find. Okay, now what we do is we look at the tangent line of f around x. So I'll draw that like a dotted line. And then we say that if we add this tangent line basically so that it passes through the minimizer x star, then we can bound the value of our function at the next iteration in terms of something involving x star, right? Because this line is going to lie above the function at our next point, just because the tangent line lies below the function everywhere. Okay, so that's the intuitive picture. In terms of the math, we just say, well, we know that from the properties of convex functions, if I look at f of x star, and that's got to be bigger than or equal to f of x plus the gradient of f of x transpose x star minus x. That's just from the property that f is convex, right? That's saying that this tangent line lies below the function. And we can rearrange that to give f of x is less than or equal to f of x star plus the gradient of f of x transpose x minus x star. That's just saying exactly that if we made it pass through x star, then it's going to lie above the function. Okay, so now we're going to take this statement right here, and we're going to plug it in for f of x up here. This was our current bound for the next iteration. Okay, so let's do that. So we're going to plug this in. we get f of x plus is less than or equal to f of x star plus the gradient of f of x transpose x minus x star minus t over 2 times the norm of the gradient squared. And now we do one kind of nice rearrangement of terms. And I'm going to write this side as the difference basically between two terms. And once I write it, you'll see where it comes from. Or you'll see why it's true, rather. Okay, so I claim that the difference between these two terms gives me this whole stuff up here. And why is that the case? Well, the x stars squared, in fact, all of the x minus x stars squared cancel out. Right, when I evaluate the difference. The only thing that's left is this thing squared. And that gives me t squared times the norm of f of x squared. And then there's a minus sign, so it's minus that. But then I multiply it by 1 over 2t, so I just get exactly this. Minus t over 2 times the norm of the gradient squared. And then the cross term is the only thing that's left. So I get this times 2. And that gives me this times this difference, because remember that was the cross term. I consider this one term. And that gives exactly the gradient transpose x minus x star. In fact, the negative gradient cancels that negative sign. And I divide by t, and divide by 2 cancels out exactly 2t. And I get that term right there, the gradient transpose x minus x star. Okay, so now we have it in a nice form because this is x plus. This is exactly our update. So we've said that the value of the function at the updated point minus the optimal value of the function is no bigger than 1 over 2t times x minus x star squared in norm minus x plus minus x star squared in norm. And now when you have something like this, what would you imagine is the next step to take? We want to make now an aggregate statement over what happened from steps 1 through step k. And I know what happens at just one step. What's that? Repeat, yeah. That's essentially the same as what I would suggest, what I was looking for someone to suggest. You could repeat it. I mean, we could also just add up these bounds. So this is telling us that, say, f of xk plus 1 minus f of x star is less than or equal to something in terms of xk minus x star and xk plus 1 minus x star. So let's just sum this up over I going from 1 to k. And we get that the sum of f of xi minus f of x star, I going from 1 to k, is less than or equal to 1 over 2t. And do I have to write all the terms in this sum? What happens here? Yeah, right. It's the telescoping sum. So essentially all the terms cancel except for the very smallest x that's positive. So I get x0 minus x star squared, because that's what's before the first iteration, minus 1 over 2t times xk plus 1 minus x star squared. Actually, I guess that's the k. Okay, Do people follow that step? Yeah. So now we're just going to cross this out because this is negative, so we can say that this is still at most 1 over 2t times x naught minus x star squared. I didn't lose, I mean, I lost something there, but it's still a legitimate bound. And finally, we use the fact that because f was decreasing in every iteration, I know that if I look at the sum of x, k, or if I look at just f of xk minus f of x star, that's less than or equal to 1 over k times the sum of f of xi minus f of x star. Right, because each one of these guys is at least as big as f of xk, because we said that we were actually decreasing in every iteration, which we could prove. And I just plug in just what I had up here with that sum, and that gives me it's less than or equal to 1 over 2 times t times k times x naught minus x star squared, which was exactly our bound that we wanted. Are there any questions about that proof? Yeah.
Yes, the t has to be less than or equal to 1 over L.
Right.
Couldn't we also say it should be less than or equal to 2 over L? It would still be strictly decreasing.
That's a great question. Yeah. So the question was here, I said that t has to be less than or equal to 1 over L so that it was decreasing. But if you look carefully, like was just suggested, if it's less than 2 over L, then actually still is decreasing in every iteration. So it's true, it will be decreasing, but we wouldn't really get the same rate. So you can try plugging in the value. If you assume it's less than 2 over L, we don't have essentially this term to work with here, which is minus, I guess I have to slide it over, t over 2 times the gradient squared. So we needed this term in order to actually continue on and improve the rate. Although we could have assumed something weaker just to say it was decreasing. Okay, so we're not going to go through a proof of everything that we claim in class, but this was one of them. This was this has a fairly standard form in terms of proofs for convergence rates for a lot of these methods, for the first order methods, I should say. And the thing to take away from it is that we use this Lipschitz assumption to simplify our lives and just kind of deal with this upper quadratic in terms of all of our statements. It would be hard to say how fast some generic function decreases after we make its gradient update, because we don't know anything about the form of f. But it's easy to say how fast this quadratic would decrease because we can evaluate it in its minimum explicitly. So that's all we did basically, is that we leveraged that fact. So that's kind of the one class of proof that you'll see in first order methods. They all use this idea of upper bounding something by a quadratic and then using the quadratic to make statements about the function. Okay, so without more questions, we'll just kind of continue on. You can trust me, or you can work it out for yourself as well. It wouldn't be bad to think about this on your own, that if you use backtracking, that you get the exact same rate. All that changes is that instead of having a t here, where that was our choice of fixed step size, we replace that by a t min, where that t min is the smallest of either 1. This is actually where you'd start the backtracking in every iteration. So that's where that comes in terms of the rate. And beta over L. Right, so basically, we can upper bound this at least by, instead of having an L here like we did in gradient descent, or sorry, rather an L multiplying there in gradient descent, we have an L over beta. So if beta is not too small, that doesn't really affect that bound too much. So basically we conclude that if we didn't choose beta to be tiny, it's very comparable to where we get with gradient descent. And it's the same rate for any fixed value of alpha and beta. It's 1 over k. Okay, so I'd be happy to talk about people in office hours or later after class about why that's the case, but we're not going to prove that one. If you're curious to know how proofs work with backtracking, you can take a look at your Boyd and Vandenberg book. They actually don't prove either of these results. They prove stronger results, or I guess the rate is stronger, but it makes more assumptions. So actually, I think I'll mention them in the next slide. But you can at least take a look at how backtracking figures into convergence analyses by reading their proofs. It's very similar. Okay, so if we assume more, we get more. That's what this slide is saying. And this one is proved in your Boyd and Vandenberg textbook, so you can take a look at this proof. So if we assume that F is strongly convex, which recall means that the smallest eigenvalue of the Hessian is lower bounded. Right, Lipschitz says it's upper bounded. Strong convexity says it's lower bounded. Then we get the sharper bound than we do from convexity. Convexity tells us that, right, if I didn't have this term here, that the function always lies above its tangent line. Here it says actually it always lies above a quadratic, which is even more strong than just saying it lies above its tangent line. So Lipschitz gradient and strong convexity together, they sandwich the function between two quadratics, one upper and one lower. And that's basically what this is assuming, that if it's strongly convex and has a Lipschitz gradient, which means that we can sandwich it between an upper quadratic and a lower quadratic, then we can prove a lot more than just this 1 over k rate. We can actually prove that it decreases like c to the k times a constant. That has to do with how far we started, where c is less than 1. So it's a whole other kind of class of, it's a whole other level of speed than the 1 over k rate. This decreases kind of exponentially fast in k. So this, like I said, you can find in your textbook. So what are some important things to know here? Let's translate this into the epsilon world. So if somebody told you that I want to have epsilon so that f of xk minus f of x star is less than or equal to epsilon, then if I know that this is bounded by like a constant times c to the k, then all I have to do is choose c to the k so that it's equal to epsilon. In other words, I have to choose k to be on the order of log of 1 over epsilon. So this was with strong convexity versus, remember, it was like 1 over epsilon without that. So there's a really big difference here. Right, so if we're doing an example where we're taking log base 10, if I tell you that I want 10 to the minus 3 in terms of my epsilon, then you need about 3 iterations on the order of that. Right? So don't think about the constant, think about how it scales. Then if I tell you that I need 10 to the minus 4 accuracy, you need 4 iterations. Right? So every time that I tell you I need another digit of accuracy, you basically go up 1 iteration. Whereas with gradient descent, you go up 10 iterations. You multiply with 10 iterations. And so there's a really big difference between how those scale. Yeah?
Is there a non-trivial example for strong convex and constant Lipschitz example?
I didn't understand the question, sorry.
Is there an example that is not a quadratic function, but it's still strongly convex and it's upper bounded by a Lipschitz?
Yeah, so I'll talk about that in a second, actually. I'll talk about these conditions in a second. But that's a good thing to keep in mind. When do they hold? So one thing you should know is that if you're ever reading papers on optimization, you might get confused because everyone calls this in the optimization community linear convergence, which is kind of weird, but that's what they call it. Because if you look at a semi-log plot, so if you actually put f of x k minus the optimal value on a log scale rather than on a usual scale, then as you plot the progress of the algorithm over iterations, it looks linear. So even though it's exponentially fast in k, it's linear on a log scale. So it's called linear convergence. And something like 1 over k is called sublinear convergence. So just be aware of that if you're reading papers. Another really important thing to be aware of is that the constant c, right, it's c to the k for some constant c, it depends on the condition number of the Hessian, which is L divided by D, its biggest eigenvalue divided by its smallest eigenvalue, in a bad way. So if it has really bad conditioning, which means it has a really big largest eigenvalue and a really smallest eigenvalue, then that's going to affect the rate really strongly. So much so that actually you may not even notice this strong convexity exponentially fast convergence, because it could be the case that c is like astronomically close to 1 if you have a really big highest eigenvalue and a really smallest eigenvalue. So you may not even notice, like I said, this exponentially fast convergence. And if you're curious to know more details about how exactly it depends on L and D, take a look at your textbook. When they prove the rates, they give the explicit form of C, so you can see exactly how it depends on those two numbers. So here's a quick look at the conditions, and then we'll take a break. So Lipschitz continuity of the gradient, remember it means that the biggest eigenvalue of the Hessian is upper bounded. So let's consider our favorite example, right? If f is just the least squares loss, so we're doing linear regression, you want to minimize f. Here beta is our optimization variable. Then its Hessian is x transpose x. So the Lipschitz constant of the gradient is the largest eigenvalue squared of x. Or I guess I'm using singular value here. It's the largest singular value squared of x. It's the largest eigenvalue of x transpose x. So if we happen to know that we're doing least squares and we wanted to use gradient descent for least squares, which I suppose you could in some case, we could take the Lipschitz constant to be 1 over, the step size to be 1 over the largest singular value of x squared. Okay, but this can also tell you that the Lipschitz constant often depends on aspects of the problem that you don't know or you wouldn't want to compute or that you can't control. If you're doing linear regression, then typically someone gives you the predictor variables, or that they come from measurements, right? They don't come from something you control. It's not like I have control over the Lipschitz constant of the gradient. It is what it is. And this can be quite expensive to compute also if you actually wanted to find it if x was quite large. How about strong convexity of f? So this is like saying that we lower bound the smallest eigenvalue of the Hessian everywhere. So go back to our same example. It means that we need this strong convexity constant to be like the smallest eigenvalue of x transpose x, or the smallest singular value of x squared. So if x is wide, if we have more columns than rows in x, which is like in a linear regression setup, means that we're in a high dimensional case. We have more features and observations. Then its smallest singular value is 0. Right, so we actually aren't strongly convex, and we don't get that exponentially fast rate in k. So whenever we're in the high dimensional case, it's not strongly convex. And even if it is positive, it's very easy to have a very large condition number, L over D, if the predictor variables are correlated, the columns of x are correlated. Okay, so this is just supposed to tell you that even in the simplest of cases, which is linear regression, these conditions can fail, or they can present themselves in a way that makes it so that even though it may be strongly convex, that rate doesn't really mean much because it's so poorly conditioned. And here's one last important comment to answer Yifei's question. So what I wrote down was that we need to have this sandwiching, right? That the smallest eigenvalue and the largest eigenvalue of the Hessian are both upper and lower bounded. And that needs to happen over all x and Rn. But if you look back at the proof, how we proved the gradient descent rate for the Lipschitz case, and if you look at the proof, say, in Boyd and Vandenberg for the strong convex case, we only need this to be true over some subset of Rn that's sometimes bounded. And that's actually the sub-level set of all points that have f of x less than or equal to the initial point you specify. Okay, because we know that we're basically decreasing the function of iteration, so we're never going to leave this sub-level set. So you'll only need strong convexity and Lipschitzness of the gradient on this sub-level set. So yes, it is not obvious that there are very many functions that are globally strongly convex, but there are a lot of functions that are strongly convex on bounded subsets. Right? A lot of the functions we discussed that aren't strongly convex, it's because somewhere in the limit, like e to the minus x, it becomes not strongly convex because the second derivative gets closer and closer and closer to 0. But if you look at like a bounded subset, it is strongly convex on that bounded subset. So that's actually the real assumption we need. It's less restrictive, but it's a detail, so you don't have to necessarily keep it in mind. Just keep in mind the kind of the rough rule of those constants and how they affect the rates. Okay, let's take a break, and then we'll resume in about 5 minutes. We've decided that we're going to go straight to subgradients today, so that you guys will have a chance to work on your homework over the weekend on the questions that involve subgradients. So what did I do? I skipped some stuff in the gradient descent lecture. Essentially, I skipped forward stage-wise regression, which was the connection of gradient descent to a statistical algorithm for regression. And I skipped gradient boosting. So this one there's a question on your homework about gradient boosting, but if you read the question, it's completely self-contained. So the explanation as to what you need to do is completely self-contained. This is just another way of formulating that same explanation. So we may get back to gradient boosting next week because it's an interesting topic, but to do that homework problem, you don't need to have seen these slides. Okay? So gradient boosting is, at a high level, is the connection between doing gradient descent and fitting kind of a flexible additive model using a bunch of weak learners. So these are both nice connections between the optimization community and the optimization world of gradient descent to what is done in statistics and machine learning. And like I said, if we have time, we'll definitely come back to some of these topics. All right, so just before we do subgradients, I'm going to say something very quickly about gradient descent. The first is that pros and cons. These will be important as we think about the other algorithms that we see in the first order method class and also beyond that class. Pros, it's simple and it's typically easy to implement. Right? You just have to compute a gradient basically. And each iteration is cheap. Just compute the gradient and then basically subtract a multiple of it from your iterate. So very cheap to perform iterations. It can be very fast if you have a very smooth problem. It can be, like we saw, exponentially fast. What are some of the cons? Well, one con is that in practice, very few problems you're interested in are strongly convex, or if they are, then their conditioning is poor enough that it's slow, which means that even though the iterations are quick, you need a lot of iterations to get anywhere. So if you want a precise solution, you need to take a ton of iterations. And a big con, which is where we're going to kind of go in introducing subgradients today and then talking about the next methods next week, is that we can't handle non-differentiable functions with gradients as we've written them. If you give me a function that's not differentiable, so far we're stuck. We don't know how to minimize it. Okay? So keep those in mind. Here's one thing to keep in mind as we kind of move towards next week also, you could ask the question, can we do better? So we proved in class this 1 over k rate for functions whose gradients are Lipschitz. And you could pose the question, what's the best we can do with methods that use the gradient under that assumption? So we're going to define a class of methods called first-order methods. These are methods that at every step, they're only allowed to update within the span of our initial guess and all the gradients we've seen. So it's allowed to choose some point in that linear subspace for its update. So it's called first order because it only uses gradient information from the previous iterations. And you can convince yourself that gradient descent is indeed a first order method. Right? It really does produce updates in this span. So now we're going to ask, what's the very best we can do with a first order method over the class of functions whose gradients are Lipschitz with constant L? We got 1 over k with gradient descent. Can we do better? And there's this nice theorem by Nesterov. You're going to see his name appear several times when we talk about the complexity of algorithms, because he's made a lot of really nice contributions that says that basically for any initial starting point and any first order method you give me, any first order method, I can find a function in the problem class so that that first order method takes at least something on the order of k squared steps. So it's actually different from our achieved rate. The lower bound for how well any first order method can do is 1 over k squared. We have a method in hand, gradient descent, that has a rate of 1 over k. So at least with respect to this lower bound, there's room for improvement. It seems like there should be a method out there, or there could be a method out there, rather, that achieves this lower bound. We don't have it yet. So we're going to see that a week from today, there actually is a method that achieves this lower bound, and more. It can solve even more problems outside of this problem class of functions whose gradients are Lipschitz. So just something to keep in mind. All right, subgradients. So the rest of this lecture is going to be about subgradients, which, as we're going to explain them, have nothing to do with an algorithm, but they're a pivotal concept. They're a really fundamental concept to understand. I would contend that this is one of the, or tied for the most important thing you should take away from the course in terms of the mathematical kind of foundations of convexity, because you'll see them everywhere. Subgradients are basically the analog to gradients when you have non-differentiable functions. And if you have a good command of subgradients, it kind of enables you to solve a ton of problems. So here's the outline. We'll talk about subgradients. We'll define them. We'll give examples. And then we'll talk about various rules, like called subgradient calculus. And finally, how subgradients can be used to characterize optimality. So remember that for a convex function, we said that the gradient provides us a lower bound on the function value if we look at the tangent line with basically the slope equal to the gradient. So f of y is bigger than or equal to f of x plus the gradient of f of x transpose y minus x. It gave us that lower bound for a convex function. So another way of saying that is that the linear approximation always underestimates the function. Remember, it's just exactly this picture. A subgradient of a convex function at some point is just any vector g that also gives us that lower bound. So the function could be non-smooth and convex. And the subgradients are just all the vectors that give us this lower bound if we were to take a linear approximation, with that vector as kind of like the slope in that linear approximation. So formally, it's a vector g such that for any y, I have f of y bigger than or equal to f of x plus g transpose y minus x. G is taking the role of the gradient when the function is differentiable. So here are some facts. It always exists. So I'm being a little bit sloppy here with saying it always exists. It always exists for convex functions on the relative interior of their domains. But usually we talk about convex functions whose domain is all of Rn, so I'm saying it always exists. If f is differentiable at x, then basically we have that the only subgradient is the gradient, and it's unique. So they coincide exactly. And this same definition applies for non-convex functions. We can have subgradients for non-convex functions, but they don't need to exist, even for differentiable non-convex functions. So how many people have seen subgradients before, just so I can get an idea? And how many people have never seen them before? OK, so it seems like most of us have seen them. What's an example of a non-convex differentiable function that doesn't have a subgradient at some point? Tell me a picture to draw. Yeah, x cubed. OK, so I didn't do a great job, but that's kind of x cubed. And where does it not have a subgradient? At 0, yeah. Because I can't draw a line here that underestimates the function everywhere. There's no line passing through that point that underestimates the function. Okay, there is here. It has subgradients away from 0. Actually, it doesn't, because this will go down. But if I consider it on a bounded interval, it would. That's not really relevant. But it doesn't have any subgradients at 0. What's that?
And to the left also.
Here, yeah, that's true.
So, I mean, if it's concave, basically like minus x squared has no.
Yeah, that's a good point too. Any differentiable function that's concave, right? It's not going to have subgradients. So that guy also. Thanks. So let's go through some examples quickly. The absolute value function. So if I have x away from 0, it's differentiable there, so it has a unique subgradient, and it's just equal to the sign of the function, right? 1 if x is positive, and minus 1 if x is negative. So it's just the same as a derivative. But at 0, there's a bunch of subgradients, and they're any value of the slope, such that if I drew a line passing through 0 with that slope, it would underestimate the function, it would lower bound the function. So if we look at basically lines of slope with either sign, they'll tell you what the range of possible slopes are. If we look at so here's the absolute value function. If you look at lines with positive slope, any of these functions work, right? But the steepest we can make that is 1. Otherwise, it would pass through the function. So we know that any positive value less than or equal to 1 works. The same thing with negative values, right? Any of these work. So anything between minus 1 and 1 is a subgradient at 0. Okay, how about the Euclidean norm of x? So here I have a picture. It's two-dimensional. So I have x1 and x2, and I look at the Euclidean norm of that vector, x1, x2. Here's a drawing of the function. If x is not 0, then that's actually differentiable. That function is differentiable, and its gradient is just x over the norm of x. All right, think about just each component. This comes from your recollection of what the derivative of the absolute value function is. Okay, and if x is 0, then the subgradient at 0 is anything that's any vector whose L2 norm is at most 1. Okay, so we can look at this a bunch of different ways, geometrically or from the definition. We looked at the last one geometrically, so we'll look at this one from the definition. So we need that f of y, which is the L2 norm of y, has to be bigger or equal to f of x. X was 0, and so the L2 norm of 0 is just 0, plus g transpose y minus x, g transpose y. That has to be true for all y. So we want to choose g to satisfy that. That would give us a subgradient at 0. Right? Clearly, we can take g to be any vector such that its L2 norm is less than or equal to 1, because then we can just use the Cauchy-Schwarz inequality and say that's at most the norm of g times the norm of y, which is just the norm of y if g is norm less than or equal to 1. Yeah?
So for the x cube, it's just 0 point or it's all the point has to be
So as we've defined it, no point of x cubed has a subgradient. Right? Because you want to go back to that picture. It doesn't less than 0 because of the fact that it's concave, basically less than 0. And at 0 it doesn't, and bigger than 0 it won't, because eventually the line will pass through the function on the left-hand side. Okay, how about the one norm of x? This is now it's like the multivariate extension of the absolute value case. So here's a picture, x1 and x2. Here's the one norm of the vector, x1, x2. So let's write this out for a second, because it'll suggest to us a rule. Right, the one norm is just the sum of the absolute values. So the answer is, and you can check this, either via geometric intuition again, or just look at the definition, that if I ask for a subgradient for any vector at any endpoint x, then if the ith component of x is not 0, then the ith component of my subgradient, gi, is just the sine of xi. And if it is 0 in the ith component, then the ith component of my subgradient must be anything between -1 and 1. So it looks like basically we just looked at each one of these guys individually. Right? We had a sum of functions, and this really only depends on the ith component, right? So it's like we just applied our absolute value rule to each term in that sum. And we'll see that when we talk about subgradient calculus, that if we have a sum of functions, we can compute their subgradients via actually an analogous rule to this. Here's one more case. If we have two convex differentiable functions, f1 and x2, and I look at their maximum, that's also convex. Remember, that was one of the rules we talked about last lecture. And if I ask for their subgradients, I have to basically consider three cases. So any time where I have one function being strictly bigger than the other, then this max is really just that one function. Like if f1 is bigger than f2 at value of x, then the max is just f1. It's actually differentiable at that point. The max is. So the subgradient is unique, and it's just the gradient of f1. Likewise, for if f2 is bigger than f1, then it's differentiable at that point, and its subgradient is just the gradient of f2. If the functions are tied at some input x, that's the only time that the subgradient is kind of interesting. It's not the gradient. So just look at this picture to think about the univariate case. It's going to be any point on the line segment joining their gradients. So in this picture, it's anything basically between those two lines. On one extreme, it can be up to that line, up to the slope of this line, which is the gradient of f1, say over here, and anything bigger than in slope that line, which is the gradient of f2. So again, you can check this. This is probably easiest to see from the definition. So here, these are just rules I gave you to remember. You can generally derive subgradients from the definition, but it's a lot easier to remember kind of these simple cases and then build your way up to subgradients of more complicated functions by using subgradient calculus, which we'll talk about in a few slides here. Subdifferential is just what we call the collection of subgradients at a point. So remember, for the absolute value function, its subgradients are anything between -1 and 1 at 0. So we just say that its subdifferential is the interval -1, 1. It's a set of all subgradients at that point. And we denote it by this partial sign, so partial f of x. It's a set of all subgradients of f at x. So some properties, it's a closed and convex set. That's actually always true even for non-convex functions. Okay, let's check this real quickly. So if I have g1 and g2 in the subdifferential of f at x, and I look at the point alpha g1 plus 1 minus alpha g2 for some value of alpha between 0 and 1, then I want to check this is in the subdifferential of f at x in order to check that that's a convex set without using anything about the convexity of f. So just by definition, if I look at f of y, then that's, we know it's already bigger than or equal to f of x plus g1 transpose y minus x, and it's also bigger than or equal to f of x plus g2 transpose y minus x. This from the definitions of the subgradients. So if I multiply this guy by alpha and this equation by 1 minus alpha, I can do that because both alpha and 1 minus alpha are positive, so I don't have to flip any signs there of that inequality. And I add these two together, I just get that f of y is bigger than or equal to f of x plus, we'll call this g transpose y minus x. Okay, so that it is convex. We use nothing to do with the function. So it's always a closed convex set, even for non-convex f's. This one we already knew. If f is differentiable, then the subdifferential contains just one point, and that's the gradient. And conversely, if it contains just one point, then it's differentiable, and that one point is its gradient. So sometimes, if you have say a convex function, you know it has subgradients, you're not sure whether it's differentiable or not, you can actually compute its subgradients, check that there's just one of them, and then conclude that is the gradient and it's differentiable. And I don't know if it's this time or next time, but we'll see an example of that. So just very quickly, there's a connection between subgradients and convex geometry, which is helpful to see because we'll be using some of these aspects and arguments we make down the line. So let's consider the indicator function of a set C. So suppose I have some set C that's an Rn. Now we're going to assume it's convex. And I'm going to look at its indicator function, which is just going to be 0 when x is in the set, and it's going to be infinite when x is not in the set. And I want to know what its subgradients are. So what are the subgradients of the indicator function? I claim that if x is in the set C, then its subgradients are just the set of all points that are called the normal cone to the set C at x, which is the set of all, I guess I'll use G, such that if I look at the linear function in G over all points in the convex set, then it's maximized at x. So basically, G transpose x is as big as you can get if you look at G transpose y over all points in the set. That's called the normal cone to that set at the point x. So this comes straight from the definition. I'll let you guys check that since we're running short on time. This comes straight from this definition. That's what it means to be a subgradient of the indicator function. And that's just going to be 0 or infinity in various cases, so it's going to give you exactly this set. But what is this set? Let's just take a look at that in various examples. So I drew this set here on the slide. So let's suppose that I look at this point. This is my set C. That's my point X. And I want to look at, let's suppose this is 0 here too. Linear functions of x. So what linear function of x, what G transpose x is such that if I take G transpose x, it's bigger than or equal to G transpose y for all points y and c. What's that line going to look like? Right, if that line points anywhere like this, then that's not going to be the case, right? Because I take basically this x. If that was G, then that inner product is not maximized, right? I can just move that. I can, for example, consider these points y anywhere here, and they're going to have a larger inner product with this vector than x is. So where does this vector have to point in order to make it so that G transpose x is really the biggest? Normal, exactly. That's why it's called a normal cone. It has to be normal to the set at x. And if that's the case, then really G transpose x is bigger than or equal to G transpose y for all y in the set. So all the points on this ray, starting here and extending outwards, form the normal cone of C at the point x. And actually, I said starting here, but it's really starting at 0, right? Because I'm just considering them to be vectors transpose x. Okay, so that's the normal cone at any point. It just looks like, as you'd expect, normal to the set. How about here? What does the normal cone look like there? What's that? Well, yeah, it is the subgradients. That's the we know that's true by the last slide. So you can spend a second to think about this on your own time, because we're short on time, but the normal cone is anything in here. So any point in this cone is in the normal cone. Any of those guys maximize the inner product with, say, this point x over all points y and c. Okay, so why is this interesting? Why do we care about the subgradients of indicator functions? I'll give you one good reason here. Eventually, we're going to prove that a point x star minimizes a function f if and only if 0 is a subgradient of f at x star. So we're going to see this in like maybe 1 or 2 slides. X star minimizes f. One very powerful thing about subgradients is that we can characterize optimality exactly just by checking whether 0 is a subgradient of a function. So why do I care about indicator functions in this context? How about if I want to know whether something solves this problem? Minimize over all x in some convex set of f of x. Well, that's a constraint optimization problem, so it doesn't quite fit the framework we're talking about, because we're talking about minimizing a function globally. However, how can I write this? I can rewrite this like minimize over all x of f of x plus the indicator function of c at x. It's the same thing, right? Because this is going to be infinite when x is not in the set. So it's not going to change the problem at all. And it's going to be 0 when x is in the set. So it's going to restrict our attention to points in the set. So now I know that I have a solution to this guy, or equivalently a solution to this guy, if and only if 0 is a subgradient of this function. Okay, and we're going to see in a second, I'm giving you a preview here because we're running out of time, that to compute the subgradient of a sum, I just take the sum of subgradients. So I just need to check whether or not x star is in, 0 is in the subgradient of f of x star plus the subgradient of the indicator function at x star. And if that's the case, then I can solve a constraint minimization problem. Okay, so if you think about it, this is actually the most generic form of a problem you can have. Minimize a function subject to constraints. That set C could be implicitly defined by a bunch of other functional constraints. It could be the set all x for which g of I is less than or equal to x for all I, and h of I is, gi of x is less than or equal to 0, and hj of x is equal to 0. It could be implicitly defined by a bunch of other constraints. This is a very general form of a problem, and now we have a kind of complete characterization of optimality for that problem. It's a bit dense, right? Because we have to know how to compute subgradients of f, and we know how to compute subgradients of indicator functions. It's just the normal cone. But still, this is actually a very powerful statement. So I wanted you to see that before we ended for the day. We're just about done. We'll just breeze through subgradient calculus, and then I'll let you guys go home. So it turns out, like I said, that you can compute subgradients by building them up from knowing subgradients of kind of more base functions, and then knowing how to propagate subgradients through a bunch of different rules. So one of them is scaling. If I ask for the subgradient of a constant times the function, where that constant is positive, it's just a times the subgradients of the function. It has to be positive because, well, currently we're thinking about convex functions, so if it was negative, it would make it concave, right? So that wouldn't even be within the realm of stuff we consider. Addition, the subgradient of a sum of functions is just the sum of the subgradients. Again, so these are pretty natural. It's exactly what's true with gradients. Affine composition. This is kind of like the closest thing we have to a chain rule for subgradients. So if g of x is f of ax plus b, then the subgradients of g at x are A transpose the subgradients of f at ax plus b. So now we know how to take subgradients if we compose f with a linear function. And this one turns out to be very helpful as well. It's a generalization of that example you saw with just two functions. But if I have a maxima of functions, I maximize fi of x over all I in some index set, say I going from 1 to m, and I call that my function f, and I ask for its subgradients, then basically I look at all functions that are active at x, which means that they achieve the maximum value. That could just be just one function. It could be several functions. It's the functions that we're calling active are the ones that achieve the maximum value among all the functions. I look at their subgradients, and I take the convex hull of that. That gives me the subgradients of the function f. So just with two functions, it was exactly our rule before, that if one function is strictly bigger than the other, then there's just one such function, so it's just its subgradient, but it was differentiable, so it's its gradient. And if both functions in my set of two functions that I'm looking at both achieve the maximum at some point x, then it's the convex hull of their gradients. And if they're differentiable, then there's just, they're subgradients. And if they're differentiable, there's just one gradient and another gradient. So it's the convex hull of 2 points. That's just the line segment joining those 2 points, which is what we saw earlier. So this is just more general than that. Okay, you can check all of these from the definition directly, but you can also trust me that they're true. But it'd be good to kind of familiarize yourself with all of these rules, because you'll be using them a lot when you deal with arguments involving optimization. Okay, have a good weekend, and we'll see you on Tuesday.